today's lecture we'll talk about two very important problems which find applications in most application areas. These are the problems of searching and sorting. I'll explain what these problems are, and we'll try to develop and analyze some algorithms for these problems. So let's talk about the searching problem first. The problem is very simple. We are given an array of n elements. These could be of any type really, and we need to find out whether another given value is present in the array or not. And let's say if it is present in the array, we return the index in the array at which this element is present, or if it is not present in the array, we can return -1. Now this problem is of course very simple, as you might imagine. All one has to do is to look at each element of the array one by one and compare it with the given element, and if there is a match, if the two values are equal, then we have found the element in the array and we know at what place in the array it occurs, and if we exhaust all the elements of the array, then clearly the element is not in the array. So this algorithm is called linear search, and clearly it takes time proportional to n to find the answer in the worst case, because in the worst case we may have to look at all the elements in the array to say to find before finding a match, or before saying that the element does not exist in the array. Let's quickly see the C function for implementing this algorithm. So this is the function search. It takes as argument an array and the size of the array. So there are assumed to be n elements in the array, and E is the element that we are searching for in the array A from A0 to A of n minus 1. So the algorithm is very simple. We have a loop that runs for I from 0 to n minus 1, that is for each index in the array, and in each iteration we compare AI with E, and if the value of AI is equal to the value of E, then we return the index at which we found this element, that is I. And if this loop finishes, that is we come out of the loop, that means that this return statement never executed, and that happened because we never found a match, and so therefore we return -1 to indicate that the element E is not in the array. So you can see that in the worst case there will be n iterations of this for loop, and each iteration takes a constant time, and therefore clearly the worst case time complexity of the algorithm is order n. So the question is, can we do better than order n for searching? And the answer is no, if there is nothing known about the elements of the array, because in the worst case we do need to look at all elements of the array at least once. So therefore we must do effort proportional to n. But if we know something about the array elements, then we can do better. So suppose the array is sorted, that is the array elements are known to be arranged in the non-decreasing or non-increasing order. Now if that is the case, and that happens in many situations, that the array is already arranged in a certain fashion, then we can actually do the search in at most order log n time. And how do we do that? The basic idea is very simple. If we compare the ith element of A with E, and E happens to be greater than AI, that means that E cannot be present from A0 to AI, because we know that AI is less than E, and since if we are assuming that the elements are arranged in a non-decreasing order, that means A0 to A minus 1, they must also be less than E. So therefore we need to now focus our attention for searching only to the part of the array which is to the right of AI, that is from AI plus 1 to AN minus 1. And similarly, if AI happens to be greater than E, that means that E cannot be present in AI plus 1 to AN minus 1, because the elements are assumed to be arranged in non-decreasing order. So if AI is greater than E, then AI plus 1, AI plus 2, etc. are also greater than E, and therefore we do not need to look at all these elements to locate E. So that's the basic idea of the well-known binary search algorithm, and this is how the algorithm works. So in each step we compare E with the middle element of the part of the array that we are looking for, at. So we basically compare E with AM, where M is equal to n by 2, that is the middle element of the array. If E and AM are equal, then clearly we have found E in the array, and we have found it at index M, so M is the answer. if E is less than M, if E is less than AM, then we restrict our search to A0 to AM minus 1, because we know that E cannot be anywhere from AM to A of n minus 1. And similarly, if E is greater than AM, then we restrict the search to the second half of the array, that is from A of m plus 1 to A of n minus 1. And so in one step itself, the problem size reduces to half, because in the next step we have to consider only half the array. And similarly, after the second step, we'll have only 1/4 of the array left that we have to search for E in. And if we keep repeating this process, in each step we keep reducing the part of the array where we have to look at by half. And so it is easy to see that in log n steps, the array size will become will reduce to 1 or 0, in which case the problem is trivially solvable in a constant amount of time. So let's now implement this as a C function. So again, the header for the function is the same. We are given the array A, the size n of the array A, that is, it has elements from A0 to An minus 1, total of n elements, and E is the value that we are looking for. These variables low and high indicate what part of the array we are currently focusing our attention on. That is, this is the part of the array in which we need to search for E. And as we saw when we discussed the algorithm, in every step this part of the array gets reduced to about half of the size that it was in the last step. To begin with, the entire array has to be looked at, and therefore low is pointing to the very first element of the array, that is, low is equal to 0, and high is the index of the very last element of the array, which is equal to n minus 1. So that's why low is initialized to 0 and high is initialized to 1, because we have to look at the entire array from indices 0 to n minus 1. The variable mid will be used to compute the index of the middle element of the part of the array that we are currently looking at. Now, the number of elements that we need to look at is high minus low plus 1, clearly. And so if low becomes greater than high, then the number of elements that are there in the part of the array that we are looking at will become 0. So in which case we'll have found the answer. If the size of the array that we need to look at becomes 0, that means E cannot be anywhere in the array. So we know the answer is answer that we need to return is minus 1. So therefore, as long as low is less than or equal to high, we keep repeating this process. We compute the middle index of this array fragment, and if E is equal to the middle element, we return this index. Otherwise, if E is less than A of mid, then, so this is mid. So if E happens to be less than A of mid, that means E is to be found somewhere in this part of the array. So which means that high should be set to mid minus 1, whereas low should remain the same, so that in the next step we focus only on this part of the array. Whereas if E is greater than A mid, then we need to focus our attention on this part of the array in the next step, which means that low should become mid plus 1, whereas high should remain the same. And when the loop terminates, that can only terminate, and if we reach this statement, we should have a return minus 1 here, which I omitted by mistake. So if this loop terminates and we reach this statement, that means we didn't find the element anywhere in the array, because otherwise we would have returned from the function using this return statement. And so if we come out of the loop, then we know that the element E is not in the array, and so we return minus 1. Let's see a couple of examples using animations to see how this algorithm is working. So let's say this is the given array 3, 4, 7, 19, 21, 23, 30, and what we are looking for is 4, which of course we know is present here. So initially low is 0, mid is 6, there are 7 elements in the array. High is 6 because there are 7 elements in the array, and mid is 6 plus 0 by 2, which is equal to 3, so mid is pointing here. So we compare E with A mid. Now E is 4 and A mid is 19, and so E is lesser, and therefore in this step high moves to mid minus 1, and then mid becomes, the new value of mid becomes low plus high by 2, which is 0 plus 2 by 2, which is 1. And so in the next step we again compare A mid with E, and this time they are equal because A mid is 4, which is equal to the value of E. So we have found the answer and the index 1 gets returned. Let's look at another example. In this case we have the same array, but we are searching for the element 22. So now 22 is larger than A mid, which is 19, and so low will move to mid plus 1 and mid will correspondingly change. So low has become 4 and high is 6, so the new value of mid is 6 plus 4 by 2, which is 5. And this time again we compare A mid with E, which is 22, and we find 22 is lesser than 23, so high will become mid minus 1. Mid is recomputed. Now low and high have become equal, but still the loop will continue, because recall that the loop condition was while low is less than equal to high. Low is still equal to high, so this condition is true. So mid is recomputed and it will turn out to be 4 again, because low and high are both 4. So we compare 21, which is A mid, with the value of E, which is 22, and E is greater than this. So that means that low will become now mid plus 1. And once that happens, in the next then the loop terminates, because the value of value of low has actually become higher than the value of high, which means that the fragment of the array that we are now looking at has size 0, and an array of size 0 clearly cannot contain any element, and so the loop terminates and we return a failure to find the element in the array. Okay, let's now analyze this algorithm that we just developed. So let's say the time taken in the worst case is Tn as a function of n, which is the array size, and as for all recursive functions, in this case we can again come up with a recurrence relation for Tn, because in every step we are reducing the problem size by half. So if n is 0, which means low is actually greater than high, then takes a constant amount of time, C1. Otherwise Tn is T of n by 2 plus C2, because if the array size is n, then in the next step the array size reduces to at most the floor of n by 2. This is not really a recursive function. Of course we could have implemented the same algorithm recursively as well, but it is still easy to express the time taken as a recurrence relation, so we have done that. And this recurrence relation, of course, should be familiar to you from the last lecture when we looked at the square and multiply algorithm. This is exactly the same recurrence relation, and as we saw last time, we can solve it to obtain the fact that Tn is order log n, which means that the time being taken by this algorithm is proportional to log n instead of n, and the number of elements of the array that we are looking at in the worst case is just log n instead of looking at all the n elements. Okay, let's now look at the second problem that we want to discuss today, and that's the problem of sorting. The problem of sorting is simply to arrange a given array of elements in some order, maybe the non-decreasing order or the non-increasing order. We will consider only the non-decreasing order. Clearly the algorithm will remain the same, only the direction of comparison will really change, and it doesn't really matter. There are a number of sorting algorithms which have been developed for this problem. What we will look at today is a very simple algorithm called the insertion sort, which is not the most efficient algorithm known for this problem. This is an algorithm which is commonly used by card players when they have a set of cards in their hand and they need to sort it. They take the next card and insert it at the right place in the cards prior to that. So that's what the basic idea of the insertion sort algorithm also is. So at any given step, let's assume that the elements A0 to AI minus 1 are already sorted. And to begin with, of course, if we set I to 1, then A0, a single element, is of course always sorted. If an array sequence of one element is obviously trivially sorted. So to begin with, this is true for I equal to 1. But at some intermediate step, let's assume that A0 to AI minus 1 are correctly sorted, but the rest of the elements are not really in their correct places. So in this particular step, what we are going to do is to make sure that the size of the sorted subsequence becomes one larger. That is, at the end of this step, we'll achieve the condition that A0 to AI are correctly sorted. So to do that, what we're going to do is to insert AI in its correct position among A0 to AI minus 1, so that after this step, A0 to AI are correctly sorted. And this procedure is repeated from for I from 1 to n minus 1. So after the first step, the first two elements would get sorted. After the second step, the first three elements would be sorted, and so on. And so after the n minus 1th step, all the n elements of the array would get sorted. Before we write the C implementation of this algorithm, let's look at the algorithm at a high level. So we are given an array of size n, and what we do is we run a loop for I from 1 to n minus 1, as we just saw, and in each iteration of the loop, we assume that A0 to AI minus 1 are correctly sorted, and AI is going to be inserted somewhere in its right place in the correct sorted order within this sequence, so that at the end of this step, the elements A0 to AI are all correctly sorted. So we need to first find what is the correct position of AI in this sorted sequence, and let's call that position as J. That is, AI should go at AJ where J is less than or equal to I, and we insert AI at the location AJ by shifting all elements which are to the right of AJ by one position, and then putting AI at the location AJ. This will become clear once we look at the details of the algorithm. So there are two sub-steps here. One is to do this searching of the correct position, and the second step is to do this insertion. So for the searching step, we can use binary search, because we already know that A0 to AI minus 1 are already sorted. But in the program that we'll write, I'll not do that. I'll use a simpler linear search, and I'll leave it as an exercise for you to implement that using binary search, which we have already seen. So using a linear search, essentially what we'll do is we'll try to find the first j such that a of j is greater than a of I, which means that a of j minus 1 was less than or equal to ai, but aj is greater than ai, and therefore the correct position for ai in the sequence is at the index j in the array. And so ai would then be inserted in the next sub-step at the index j. Note that it may turn out that j is equal to I. Now j is equal to I will happen when ai is larger than all the elements a0 to ai minus 1, and that is, it happens by chance that we sorted just the first I minus 1 element, and the ith element was already in its right place. So in that case, of course, nothing needs to be done, but we must ensure that our algorithm works correctly even in this case. So here is an example of the insertion step. So let's assume that these sequence is already sorted. So I is 6, which means that the sixth element of the array has to be inserted at the right place, and A0 to A5 are already sorted, as you can see in this example. Now j is 3 in this example, because 10 should really appear at this location. Now the way the insertion will happen is, let's move out this 10 and store it in a temporary variable, and then after that shift this element one step to the right, again shift the next element one step to the right, and shift the next element one step to the right, so that now 10 can be safely stored here, because the old value stored here has been shifted here, the value stored here has been shifted here, the value stored here has been shifted here, and so 10 comes here. So that's the insertion step. We're now ready to look at the implementation of the algorithm. So we have this function insertion sort, which has no return value. takes an array A and an integer n and sorts the array A. Note that this function is going to modify the values of elements of A, but and it doesn't return the new value, but that's all right, because the array, as you know, is passed as the starting address of the array is really passed, and when an element of that array is accessed or modified, it is accessed using its address, and so therefore the change is reflected in the array of the calling function. So we have these local variables I, j and t. Now this is the outer loop, which runs for I from 1 to n minus, and for each value of I we have to first do the search. The search is quite easy. So we start, so essentially what we have to do is for j from 0 to I minus 1, we have to find the first value of j such that aj is greater than a of I, because a of I is what we are trying to insert here. So we start from 0 and we proceed towards a of I minus 1, and as soon as we find a j such that aj is greater than ai, we break from the loop. So when we come here, either aj is greater than ai, and that's why we broke from the loop, or it is possible that j is equal to I. If j is equal to I, that means that ai is already in its correct position. It is already larger than all of a0 to ai minus 1, and nothing really needs to be done in this case. So this is the insertion step. Note that this step happens even when I is equal to j, but as we'll see that it works correctly even when I is equal to j. So we first move the value of ai to a temporary variable, and then for all locations of the array starting from I minus 1 going back right up to j, this should be k minus minus instead of plus plus, we move the value of ak to the location ak plus 1, and so all the elements of the array starting from I minus 1 and going back up to j, they get shifted one place, right? And then finally the location aj is given the value t, which was the original value of ai. Note that if I happens to be equal to j, then what will happen is that t will be assigned ai, and then this loop will not run at all, because the initial value of k is I minus 1, j is equal to I, so I minus 1 is not greater than equal to I, so this condition will become false in the very first iteration, and so therefore the loop body will not execute at all when j is equal to I, and so therefore all that will happen will be these two assignments, t assigned ai and aj assigned t. Now since j is equal to I, all that happens is that t assigned ai and again ai assigned t, which has no effect really, because the same value is assigned back into ai. So that is as we want it to happen. So when this outer loop terminates, when it has run for all values of I from n1 to n minus 1, the array is sorted and the function returns. Let's now analyze this algorithm to find its time complexity. The outer loop, as we know, runs for I from 1 to n minus 1 for different values of I, all values of I from 1 to n minus 1. And let's look at one particular iteration of this outer loop. So let's look at the iteration where for some particular value of I, that is the ith iteration of the outer loop. Now in the ith iteration of the outer loop, this loop as well as this loop will run at most I times, because we may have to do this I times, because the element which is greater than I may not be present at all, in which case we need to look at all elements from a0 to ai minus 1, and the worst case for this step happens when the value of j turns out to be 0 itself, because then all elements from a0 to ai minus 1 need to be shifted, so a total of I elements get shifted. So and if you think carefully about this, the number of times that this loop will execute plus the number of times this loop will execute will actually always be equal to I. So therefore the time taken in the ith iteration is, in the worst case, is C1 times I plus C2, that it is proportional to I plus a constant. Note that if we had made the search step as a binary search step, instead of using linear search, if we had used a binary search over here, then the amount of time taken in this step in the worst case would be log I, and the amount of time taken in the worst case over here would be order I. But if you add these two up, that would still be order I. So which means that the amount of time taken in the ith iteration would not really change in the order notation, and therefore the overall time taken would also not really change in the order notation, even though using binary search is of course slightly more efficient. So for each iteration of the for ith iteration of the loop, the time taken by the iteration is proportional to I, or we have denoted as C1I plus C2, and therefore the total time taken is C1 times 1 plus C2 for I equal to 1 plus C1 times 2 plus C2 for I equal to 2, and so on up to I equal to n minus 1. And so if you add up all that, C1 will have a coefficient of 1 plus 2 plus up to n minus 1, and C2 will have a coefficient of n minus 1, and the C3 time might be some constant amount of time required in addition to the outer loop, for example for initialization and overhead of the function call and so on and so forth. So now if you, this is an arithmetic series, and if you add this up, it turns out to be n times n minus 1 by 2, which is a constant times n square plus lower order terms, and so this entire thing is constant times n square plus lower order terms, and therefore in the big O notation this is order n square. So this is the end of today's lecture. In the next lecture we'll talk about a new data type in C that we haven't looked at so far, which is the structures type.